Hi, welcome back to the Mathematics channel, the only channel on YouTube where we are absolutely addicted to numbers. Now, the last video in this series, which I suggest you check out, was on Gaussian elimination. In particular, we learned about Gaussian elimination and its foundations, as well as how to crunch the numbers, how to actually solve a set of linear equations using Gaussian elimination. After watching that video, you must be thinking that there is no clear or easy, intuitive way of representing Gaussian elimination, that whole augmented matrix and all the operations we're doing. There's no clear way to represent that geometrically. Well, you would be wrong, and today's video is to prove just that. Today's video is about the geometric interpretation of Gaussian elimination, how it actually looks, how it plays out in a vector space. Now, before we begin, I highly suggest you check out 3 Blue 1 Brown's course on YouTube on linear algebra. It's completely free, and today's video is going to pull a lot of its foundations, so you will not be getting the complete package or the complete understanding of this video without previously going through that. So I highly suggest you go through that. In fact, after watching his video on Kramer's rule, and in particular when he said,
Also, from a purely artistic standpoint, the ultimate result here is just really pretty to think about, way more so than Gaussian elimination.
This actually directly inspired me to create this video, because I thought there actually is an intuitive way of geometrically representing this. Why not show it? Now, before we begin, let's do a quick recap. We know that manipulating I cap and j cap and taking that as a vector or a linear transformation, we can transform the entire vector space. So any transformation of the vector space, basically this grid, which is basically all of the vectors possible, transforming these vectors can simply be represented by how we're transforming I cap and j cap. All of these examples are for various linear transformations. You can see how they're moving all the vectors. Another thing that we have to remember is that a linear transformation is any transformation, in essence, that keeps all of the grid lines parallel and the same distance apart. It does not change that. It should also keep the origin in place. Following these rules, all of these transformations you're seeing right now are linear transformations. One final recap: any set, any system of linear equations in n number of variables can be represented in the form of matrices. For our video, we're going to focus on 2 variables, just for simplicity's sake. Let's take this example. 0x plus 2y is 4, 1x plus 1y is 5. Representing this in the form of matrices gives us our geometric understanding of what we're trying to find. We know b, we know a, we don't know x. X, after being transformed by a, goes to b. So we need to find that vector x, which after going through the linear transformation turns into b. Now, as we learned in our previous video, Gaussian elimination just takes the vector b and the matrix a and turns them into an augmented matrix, just writes them together. After writing them together, we perform a set of rules. These 4 rules. E refers to exchanging or swapping 2 rows. M refers to multiplying or scaling a row. L refers to taking one row and doing something to it, i.e. multiplying it by some scalar, and then adding or subtracting it to a lower row or a row below it. Similarly, U is the same as L, but upwards, so taking a lower row, multiplying it by some scalar, and then adding it to the upper. Using these elementary row operations, we can transform our matrix into a reduced row echelon form. If you watched a previous video, you would know that I'm doing a little bit of a white lie here. We're following Gauss-Jordan elimination, not Gaussian elimination. But this is because it's much easier to visualize Gauss-Jordan elimination before visualizing Gaussian, so bear with me for some time. Now, writing these as separate matrices and vectors, remember, doing an elementary row operation on the augmented matrix is just the same thing as doing it to both A and B. Now let's see how these operations look geometrically by taking some examples. We do this by taking the identity matrix and just performing that operation. For exchange, it just flip the axes. For multiplying, it's just shrinking or enlarging any one of the axes. And for our third and fourth rule, the upper and lower rule, it's just shearing the axis. You can probably see that all of these are linear operations. The origin is not moving, and all of the grid lines are remaining parallel and equally distant. But what were we doing just now, getting those random matrices? Well, performing the elementary row operations on I-cap and J-cap, the identity matrix, converts those row operations into a linear transformation matrix. Now we can use that matrix, and multiplying it by any random vector v will give us the same result as if we just performed that row operation. I suggest you rewind this part of the video and carry out the math yourself, or work through it in your head, just to play around with this idea and get a better grasp of it. So what have we done? We've taken ax is equal to b, and we've multiplied it by some other matrix t. T is invertible since these are all just linear operations. So whether I do e, m, whatever I do, if I keep doing these operations, keep flipping rows and keep subtracting the rows, whatever I do, I can always go back. I'm just multiplying a bunch of matrices. I'm just changing I-cap and J-cap again and again and again. What do we have to do? We have to find the unknown vector x, which after transforming, after being multiplied by the matrix A, becomes b. Performing the relevant row operations, you can see b is walking back to x. We're bringing back I-cap and J-cap from their transformed versions back to normal I-cap and J-cap. How are they transformed? They were just multiplied by A, right? That's what the matrix does. A was the linear transformation that multiplied I-cap and J-cap to get that. We're just walking them back. We're reverting A. You can see by doing this, whatever vector we end up with, that is the vector which we want as our answer. Let's look at how A changes as we perform these operations. After multiplying EMU through our Gaussian elimination process, we've transformed A back to the identity. We've reverted it. So no matter what operations they are, we can combine them all and refer to them as T, right? All we've done is multiply a bunch of matrices, a bunch of linear transformations. If you can just multiply them all together on the left-hand side, we'll get T, which is a single matrix which performs all of the operations at once. B comes back to X. Looking at T and looking at what it did, you can probably intuitively understand by now what T is. After multiplying by the matrices which we have applied Gaussian elimination with, we get the identity matrix. So T multiplied by A gives us the identity matrix. You can clearly see that T is the inverse of A. We have solved the equation, and we've also found a neat way to find the inverse of A, which is also one of the various uses of Gaussian elimination. This is even more clear when we look at the graph again. Watch it play out and play around with this idea in your mind. Now that was beautiful, but it was Gauss-Jordan elimination. Let's look at how Gaussian elimination looks geometrically. Remember, we're creating a row-echelon matrix now, not a reduced row-echelon matrix. Basically, we need to create a staircase pattern. For the 2 by 2 matrix, this just means the bottom left value has to be a 0. Before we go through it, let's look at random examples and play around with how a row-echelon matrix behaves. We can see that taking any random vector x and multiplying it by a, where a is a row-echelon form, to get b, we can see that b's height is simply x's height multiplied by j cap's height. J cap's height is 2. Multiplying this by x's height, we get b's height. Try to look at the matrix A and figure out why this is true. One way to think about it is that I cap is being transformed with 0 on its y, so with 0 height. All of the y transformation in the linear transformation A is coming from that value of j cap, the bottom right value. Let's look at a concrete example now. Again, we want to find the matrix X that after the transformation gets B. Let's walk back until we get the row echelon form. We need to find X. Now, since we know that the height of X, or where it lands on the y-axis, multiplied by the bottom right value, which is in the matrix A, so the height of j cap after being transformed by matrix A is simply the scalar which is multiplied to x's height to get b's height, or 4. We don't know x's height, but we know b's height is 4, and we know the scalar was 2, so something was multiplied by 2 to get to this 4. Simply divide it by 2 and we get the answer. So x's height is 2. X is multiplied by the I cap transformation and y is multiplied by the j cap transformation. We can see that all of the height in the resultant vector is simply coming from that j cap y value, which is a22. We can use this to find y. After we know y, it's very easy to find x. It just takes some vector subtractions. Subtract y into j cap, or the vector j cap scaled by y. Subtract that from b, and wherever you land, that is the value of x, the scalar x, multiplied by I cap. We know where we're landing. We know what I cap is. We can simply find the scalar x by looking at how many I caps fit into that space. In this case, it's 3, so the value of x is 3. We've just solved a set of linear equations using Gauss-Jordan and Gaussian elimination and seen how it looks on a graph. Basically, we know that some vector x was transformed by A to get B. To find this vector x, we're just walking back the vector B step by step until the linear transformation A is cancelled out, or it's cancelled out enough such that we can find x and y. That's all that Gaussian elimination is, walking back. If you found this video even a little bit enlightening, please leave a like so that I know, and subscribe if you want to.